This is an introduction to projectile motion. Projectile motion is defined as the motion of a body with an initial velocity acting under the constant acceleration of gravity only. Some of the commonly cited applications of projectile motion are sports applications such as the basketball throw, weapon applications such as artillery fire, and even applications in fluids such as the arc of the flow of water in firefighting. Incorrectly cited applications are missiles and other powered rockets, that while experience gravity while in flight, have another dominant force acting upon them. Hence, the laws governing projectile motion cannot be used on their own to predict their motion. Unpowered flight for airplanes is also not projectile motion. When an airplane loses power, it becomes a glider, and while being pulled by gravity, it is still aerodynamic, generating lift due to airflow around its wings. Swings on a playground accelerate due to a component of gravity, but again, because there is another force acting, in that case tension, it cannot be considered a projectile. Projectile motion describes a path that is parabolic in nature. Because of acceleration downward, the velocity is going to change direction and magnitude in the vertical direction. However, the acceleration in the horizontal direction is always zero. To understand the equations governing projectile motion, please review the equations of kinematics with constant acceleration. If we insert zero horizontal acceleration, then we see that the horizontal component of velocity will be constant. Hence, the equation governing horizontal displacement is simplified. In the vertical direction, we replace acceleration with negative g. The negative indicates the direction downward, and the value of g is the acceleration due to gravity near the surface of the Earth, 9.8 meters per second squared. To keep track of the components of velocity, it is important to always draw the picture. You must set up the coordinate system and calculate the components using trigonometry. Once the velocity is broken into x and y components, you can use the kinematic equations independently of each other, with the exception of the shared variable, time. In some problems, it will be asked that you give a final velocity. Because velocity is a vector, you need to specify both magnitude and direction. You can use the Pythagorean theorem and the arctangent function to do this. A common strategy in most projectile motion problems is to break the problem into separate parts around the maximum height. Maximum height is defined as where the vertical component of the velocity is 0. This allows simplification of some of the kinematic equations to solve for time and displacement to maximum height. Note that projectile motion does not have to be along a level surface, nor does it imply that the impact point has to be flat either. One can use the x and y coordinates of the final impact point regardless of the shape of the surface there. One can also calculate problems where the final position and velocity are given, and you have to back calculate initial velocity and initial position. Notice that the physics and the geometry of the problem have not changed. You merely have to use the same kinematic equations and just rearrange them algebraically for the unknown variables. We will cover examples of these scenarios in another video.